Sorry.
Sir,
Your
ZP is
this
a field. ZP is a
Yes,
field.
yes, 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 yes. I'm starting with that only. So in the
Okay, sir.
last lecture, it was you who asked me whether we can write or how to write or how to find like a multiplicative inverse of a non-zero element in ZP. So you know that ZP is a field, right? So
Yes,
ZP
sir.
is a field when P is prime, ZP is a field. So let us start with this. So here on that day, I said that you asked me whether we can write multiplicative inverse of a non-zero element in terms of A or not. The answer is that there is no such formula. So I check, I look for it, and I did not find. And I asked my colleague also, and they said that there is no like explicit formula one can write for multiplicative inverse in terms of x. For example, what I'm saying is that you have ZP where P is prime, and if you take any A which is non-zero in ZP, then you know that since it's a field, there exists X in ZP such that AX is equal to 1, so 1 modulo P, right? So you can write it like this. Okay. Now the question is whether you can, so there exists such a X. Why such a X exists? Because if A is non-zero, P is prime, then A and P, and A is element of ZP, so A and P are co-prime. So that means GCD of A and P is equal to 1. And this implies that there exists such a X not equal to 0 in ZP such that AX is equal to 1. This is because of the division algorithm. If you just apply division algorithm, because of this, you can find such a X. Now, if suppose you want to write X explicitly in terms of A, then what you would do and what one would do is that like AX, what you know is that AX uh, is equal to 1 modulo P. What does it mean? It means that AX minus 1 is divided by P, right? So AX minus 1 divided by P means there exists some integer k such that AX minus 1 divided by P equal to k. But if you want to write it in this way, then it would be like AX equal to PK plus minus 1. So plus 1 you can write. So according to this, since A is non-zero, you can write AX as A inverse PK plus 1. But then the problem is that this X, this should be in ZP. You don't know whether in this form it is an integer or not, and it belongs to ZP or not. So this way of saying or this way of writing X is not correct. So this whatever have written here, this is not correct. I mean, this I cannot guarantee in this way, or I cannot claim that I don't have a proof to say that X belong to ZP and uh, it's an integer. It's an integer. It belongs to ZP. So what you do is that you apply. You know that there exists such a X, such that AX is equal to 1 modulo P. So what you do is that you just try for all non-zero X. So you start from here X. You start from here. Uh, so it's like AX, what you want is that AX minus 1 should, P should divide AX minus 1. And then what are the candidates for X? The candidates for X are 1 to P minus 1 because it should belong to ZP. So you consider one by one, you check for every X. So you take X equal to 1 and then check A is given and then whether P divides AX minus 1 or not. And then you do for 2 and then you so on for, you check for all the possible candidates, and whenever you find that it divides X minus 1, then you say that it is the inverse. Since inverse is unique in a field, it's a unique. So there is no such formula. The answer to your question is there is no way to write explicitly the multiplicative inverse, that means X, in terms of A. There is an algorithm which is the division algorithm. which you can use and you can find this multiplicative. Is it okay now?
Okay, sir. Thank you, sir.
Yeah. All right. So let us move forward. So in the last class, we talked about some algebra of linear transformations. Like you can add two linear transformation, and it would again be a linear transformation. You can multiply with a scalar, and the scalar multiplication is again a linear transformation. And then we also saw how to write matrix of a linear transformation. Not only that, we also saw, so what we saw is that we first started with a linear transformation from a finite dimensional vector space V to another finite dimensional vector space W. And then for that we found, when we fixed two bases, one for V, one for W, then with respect to these bases, we found matrix representation of the linear transformation. But then we also saw that if suppose instead of starting from a linear transformation, if we start with a matrix, then also there is a way to find so if suppose we have a matrix A of size m cross n, and we have two vector space, one is V of dimension n, one is W of dimension m, then if we fix two bases, one for V, one for W, then we can define a linear transformation from V to W such that the matrix of T with respect to these two bases is the given matrix A. So somehow we know that there is a way to go from linear transformation to matrices, and there's a way to go from matrices to linear transformation. Right? And then at the end, I define isomorphism. So isomorphism is just it's a linear transformation from a vector space to another vector space, which is also a bijection. It's one and on two. All right. So from now, from here, we'll start today's lecture. So let me remove this stuff first. We can start from here. So then I said that every n-dimensional vector space over field F is isomorphic to Fn. That means n copies of F. So, and you said that yeah, it's true because you can always define a linear bijection or an isomorphism from the vector space to Fn by assigning by you just fix a basis and then assign every vector to its coordinates or its matrix representation. That way you can say that every vector space V of dimension n is isomorphic to Fn. Now next, these are very easy results, so you will see that the proofs are not difficult, but we should know that these things are there. For example, if we have two, so let me write this first. So two finite dimensional vector spaces are isomorphic if and only if. So if I write this notation I double F, that means it's if and only if. Okay. Sometime I write if and only if explicitly. Sometime I write in this way. So both have the same meaning. So if and only if they have the same dimension. So why this is true? So this is if and only if. So you have to check both ways. So let us check first the if direction. So two finite dimension vector spaces are isomorphic. So suppose that you have two finite dimension vector spaces, let's say V and W, and they are isomorphic. So let's say there is an isomorphism between from V to W, right? Because they are isomorphic. So up to this is given. Now how to show that they have the same dimension? Can you tell me? It's very straightforward.
Sir, we keep this student.
Your voice is breaking.
Sir, we keep this student V1 V2 दो दो million.
So V की basis ले लेंगे फिर?
Yes, sir. We keep this student V1 V2 and the basis like put up the basis.
Actually, your voice is not clear. I'm not able to understand. because it has noise.
सर
Yeah.
सर इनके बेसिस लेकर क्योंकि आइसोमॉर्फिक है 1 1 है तो
क्या
बेसिस
क्या
सर इसके बेसिस कंसीडर कर लेंगे वी और डब्ल्यू
V के बेसिस कर लेंगे, W के कर लेंगे, फिर
सर 1 1 की आइसोमॉर्फिक है तो ये 1 1 तो होगी
so isomorphism तो दिया हुआ ही है. So isomorph by
यस सर
definition this T is 1 1 and on 2. So from
यस सर
this you want to conclude that dimension of V is same as dimension of W.
सर टी बीटा होगा
सर
डिपेंड करेगा
यस सर सर वी के
Yeah.
बेसिस को कंसीडर कर लेंगे फिर डब्ल्यू के बेसिस
सर मैं
सर ये आइसोमॉर्फिज्म गिवन है तो ये बाइजेक्टिव लीनियर ट्रांसफॉर्मेशन होगा. तो अगर 1 1 हम देखें तो सर डायमेंशन ऑफ वी शुड लेस आर इक्वल टू डायमेंशन W, और फॉर ऑन 2 देखिएगा तो डायमेंशन ऑफ वी लेस आर इक्वल टू डायमेंशन W. तो बोथ को अगर इक्वेट कर देंगे तो डायमेंशन V इक्वल टू डायमेंशन W.
So yeah,
Yes,
so
sir,
it
this one.
follows by rank nullity theorem. You can say that you know why it is, because you know that there is a, so this T is an isomorphism, that it is 1 1 and on 2. So dimension of V by rank nullity theorem, you know that it is rank of T, or you write it in this way, range is dimension of null of T is n plus dimension of range of T. But you know that T is 1 1, so dimension of null of T is 0. And then you know that T is on 2, so dimension of range of T is actually equal to dimension of W. So from here you can say that dimension of V is equal to dimension of W. So this is straightforward. Now the other direction, if suppose we have we have two vector spaces which have the same dimension. Now how to say that they are, how to show that they are isomorphic? So it is given that we have two vector spaces V and W. Dimension of V is equal to dimension of W. Now you have to show that they are isomorphic. So that means there you have to show that there is an isomorphism.
सर वी के बेसिस को डब्ल्यू के बेसिस पे मैप कर देंगे.
So you are saying that you take, because they have the same dimension. So let's say we have a basis, let's say V1 to Vn for V, and W1 to Wn for W. Now you are saying that the map, so you define T from V to W such that T of Vi goes to Wi. Now what would be this map? Can you tell me? This is what you want, but you have to give me the map. What it would be?
I runs from
T
1
of
to n.
0, T of 0 and V should map in T of 0, 0 of W.
No, so what I'm saying is that you have to give me the mapping that works for every. So it's a mapping, that means every vector of V is assigned to some vector of W. So you have to give me that.
टीवी इज इक्वल टू
सर
Hmm?
इसकी
समेशन अल्फा
सर
डब्ल्यू
लीनियर कॉम्बिनेशन ऑफ द
Yeah.
वेक्टर
Is this, and then you send it to alpha I Wi. Right? So this linear transformation, so you already know that such a map is a linear, is a such a this kind of map is unique, that sends these Vi's to Wi's. This is linear clearly, and you can check that this is also, and it's not only linear, this is an isomorphism. This is 1 1 and on 2. Okay, so then you can show that clearly T is linear. You just have to show 1 1 and on 2. So that is very easy to check why this is 1 and on 2. Can you tell me why this is 1 1 and on 2 quickly?
द रेंज ऑफ टी डायमेंशन ऑफ डब्ल्यू के इक्वल था.
Yeah, so you can use rank nullity also, and there are several ways to show this. Either you use rank nullity or you just use the definition of 1 1 and on 2. And anyway, so this was easy. So now using this result, we show that we know that um, is- the set of all linear transformation from a finite dimension vector space V to another finite dimension vector space W. Suppose V and W are finite dimensional, then we collect all the linear transformation from V to W, and then we are calling this set as V LVW, right? LV comma W. Now, using this result, the result just stated, using this result, we will show that this is a, of course, this is finite dimensional. We will show by showing that there are two ways to show. Either in order to show that it is finite dimension, either I use this result. That means I show that this space is isomorphic to some finite dimensional vector space, or I explicitly find a basis for this, which has only finitely many vectors from this set, right? So let me give you one, and then you tell me idea for, for the other proof. Okay? So let me write this first. So suppose that we have a vector space V and a vector space W. Okay, so let's say we have V and W, two finite dimensional space, and let's say we have a basis B for V and B dash for W, right? So these are bases. So V and W are two finite dimensional vector spaces, and B and B dash, they are the basis of V and W respectively. Then this map, which I denote by this M, script M, from the set of all linear transformation from V to W, that means L, V, comma W, to the set of all matrices. So is it okay? So let me just change the notation, otherwise I might confuse. So let us define this linear transformation by let's say G. Okay. So this is then this function G from the set of all linear transformation to set of all matrices of size m cross n. So you assume that dimension of V is n and dimension of W is m, defined by this, that you take any transformation here and send it to its matrix representation. Right? This you can show that this is an isomorphism. So that means you take a linear transformation, you fix two bases, one for V, one for W, and then you define this function from the set of all linear transformation to set of all matrices of size m cross n. You define this function, and how it is defined, you just send every linear transformation to its matrix representation with respect to the given basis, and then you can show that this function is actually an isomorphism. That means it is linear 1 1 and on 2. All right. So let me instead of writing B dash, just to make it write it more precise, let me write that this V1 to Vn, this is B, this is a basis for B, and B dash, let's say W1 to Wm, this is a basis for W. Okay, so this way from here it is clear that dimension of V is n, dimension of W is m. All right, so we have defined a rule that assign element of linear transformation or set of linear transformation to set of matrices. So we have to show that it is an isomorphism. Now, first we have to check that it is a well-defined thing. So whether this map is well-defined or not, whether it is a function or not. Once we convince that okay, this is a well-defined thing, then we check the linear, whether it is linear or not, If it is linear, then we check whether it is an isomorphism, that is 1 1 and on 2. Okay. So first check is the linear well-definedness. So check well-definedness. That this map is well defined or not. So how to check that this map is well defined? Can you give me some idea? Mathematical way to check that. So if we are given a function, then how to, so this is G is a function, right? So we have to show that this function is well defined. This is actually a function. So we don't know this is a function. We have to check that this is actually a function. That means well defined thing or not.
So if we have for any x,
Two
it should
elements.
more than one element.
So how to show that?
So we take two elements from domain and we show and put them equal, and then we show that their image will also be equal.
Yeah, so that's the way. That's the mathematical way. So you take any two element. Let's say in this case. So if I write for this function, then what it would be? So if I say that, let's say t and s, they are two linear transformation, and assume that t is equal to s, then you have to show that g of t is equal to g of s. That is what you have to show. All right, how to do that? So t is equal to s. So you have to show that what you have to show. You have to show that g of t. So let me just write it here, then I'll erase. So you have to show that g of t is equal to g of s. But g of t is what? So you have to show that matrix of t, this thing is equal to matrix of s. Right? This is what you have to show. And assume that this matrix of t is denoted by tij, and this is denoted by sij. Okay. So this we have to show that g of t is equal to g of s. So if we show that tij is equal to sij for all ij, then we are done. Agree? So what we have to do here, what we are given? So we are given t is equal to s. Okay. Now what does it mean? The two linear transformation t and s, they are equal. What does it mean? So how to show, how to get that g of t is equal to g of s from t equal to s? That means we have to show that this thing is,
So
they
T
are
of
equal.
vi is equals to S of vi for every vi belongs to capital V.
Right. So from here you can say, because they are equal, that means their function, their value at every point, every vector is same. So you can say that you just, it is enough to show that C for the basis vector. So let's say T of Vj, from here you can say that T of Vj is equal to S of Vj, where V1 to Vn, they are the basis vectors. So you just see for basis vectors. This is true for all Vj, for all j. But then from here, what you can say? From here, what you can say?
range.
So you
Like
can
it
write,
will equal to something wi.
yeah. So this you have to make sure that the Tijs and Sijs are they appear here. So you can write, you know that TVJ, you know the matrix representation. So you can write this T of Vj as Tij Wi I equal to 1 to m. And similarly here for this SVJ, it would be Sij Wi I equal to 1 to m. Right? But from here you can write that it is summation I equal to 1 to m Tij minus Sij Wi equal to 0. But can you say from here that Tij is equal to Sij?
Yes, sir, because Wi is the basis of W,
Yes, they are
then it
basis, so
is
they are linearly
linearly equal.
independent. Right. So from here you can say that Tij equal to Sij, and this is true for all I equal to 1 to m, and j is equal to 1 to n. So from here, this implies that g of t is equal to g of x. So this is a well defined thing. Now similarly you can now show that M is linear, M is 1 and M is
So G
1
is
2.
linear. G is 1 1.
Oh, sorry. So I'm using this notation G. Yeah, thank you. So G is linear, G is 1 and G is 1. Okay, so this you can verify. This I put this as an exercise. This is a straightforward thing. How to show that G is linear? For this, you can use the fact that if you remember from previous class exercise, if you have two transformation, so if you take the matrix representation of T plus S, then it is equal to the sum of their individual matrix representation, and similarly matrix representation of alpha T is equal to alpha times matrix representation of T. Because of that, linearity follows. Then oneness is similarly you can show, and you once you have oneness, then you can also prove that G is onto. G is onto is also we have shown, right? If you look at observation from previous lecture, G is onto means what? G is onto means you have to take a matrix here. You have to take an element, that means a matrix from here, and then you have to show that there is a linear transformation such that the matrix of T with respect to this basis is the given matrix that we have done in the previous class. So using that observation, you can show that this is onto. So this map is clearly linear and onto because of the observation we made in the previous class. You just have to show G is 1 1. This you can just use the definition and you can show. So this I put as an exercise, right? So this is an easy exercise. Okay, so let us so let me state one more result. So if we have a instead of, so if suppose W is equal to V, so that means if we just talk about linear operators, that means linear transformation from V to V itself. Okay, so if we have a finite dimension vector space, let's say V, and T is a linear operator on V, then T is 1 1 is same as T is on 2. Then T is 1 1 if and only if T is on 2. Do you agree with this?
Yes,
If
sir.
V is finite
Yes,
dimension,
sir.
Yes, sir.
this
Yes,
is
sir.
very straightforward because of rank nullity theorem. So if we have a finite dimension vector space, then 1 1 is, and if we have a linear operator, so a linear transformation from V to itself is called a linear operator. Okay. So if we have a linear operator on a finite dimension vector space, then 1 1ness and ontoness is the same. So here the assumption that V's finite dimension is important. I'll give you example where it is not true if V is not finite dimensional. But before that, let me ask you this thing. You know what is an invertible function? So first you tell me what is an invertible function.
Isomorphism
1
1
and
1
2
1 1
and on
1 1 and
onto
on 2.
Z.
So a function which is 1 1 and on 2 that you call as say invertible function. Is there any other way? So if suppose I don't want to use this 1 1ness and ontoness to define invertible function, then how would I do? So f is called invertible if, so let's say let me recall this. Okay, this is for function first, and then we'll talk about linear transformation. So let us recall this. Okay, recall from your basic learning. So let's say we have a function f from V to W. Okay, then we say that this function is invertible. Now, what do you mean by that? Invertible
Sir, if there exists a function g from v to
right,
w such that
P to
f of
W, just
sir w to
W2. Okay,
yes such
such
that
that
f of g equals to g of equals to identity.
is equal to identity. All right. So if I have you heard about right inverse and left inverse? Or like so
Yes,
for
sir. In
example,
group theory, like right inverse and left.
there is this kind of concept. So in general, when you define invertible function, you can do it in this way. So if suppose we have a function f from v to w, then it is called invertible if there is a function g. As you said, it is identity, but then the thing is that identity on what? So for example, if you look at, so you said that f of g is equal to I is equal to g of f. This is what you said. If there exists such a g from w to f, w
Sir,
to e.
if
So you have to,
compose G equals to I of W and G compose if
yes,
I of V.
yes. So that's what you have to differentiate. So this is an identity on w. This is an identity. Anyway, so let me write this for others also. So what is she saying is the following. She's saying that if a function, we have a function from v to w, then it is called invertible. If there exists a function g from w to v such that gf, or you can write it as g of f, and g composition f equals the identity function on v, and fg is equal to, which you can write at f of g equals the identity function on the on w. If this is the case, then G is called the inverse, right? You say that G is the inverse of. This is what you have learned. So I'm just recalling what you did. But is the inverse always unique?
Yes, sir.
Is the inverse always unique? Okay, so we don't know whether every function is invertible. Of course, every function is not invertible. We have several examples. So every function is not invertible. But if the function is invertible, then the inverse is always unique. That you can say. So we don't know whether a function is invertible or not, but what we can say is that whenever inverse exists, it is always unique. So you can say that inverse of a function is unique. Right? So how to show this? Quickly, can you tell me an argument for this? Why inverse of a function is unique? So let's say how to show that. So let's say f is the function, and assume that g and g dash, they are two inverses of f. Okay, so let the g and g dash be two inverses of f. Then we have to show that g is equal to g dash, right? Now how to show this? This is not difficult. You can show that g, you have to show g is equal to uh, f, and then you just use the definition of the inverse, the invertible function. So you know that this you can write as g composition with iw, that means identity function on w. Then you know that this is actually equal to f g dash, because g dash is also an inverse, and then this is equal to gf g dash, right? But then this is an identity function on v g dash. then it is just zeros. The inverse of a function is always unique. Since it is unique, and therefore we can fix a notation for this, and thus denote the inverse. Thus denote it by f inverse. So denote the inverse of f by f inverse. So this is the notation we can fix because it is unique. So we can fix this notation for inverse of f. All right. Now if we talk about linear transformation, so linear transformations are also functions. They are function addition on top of that they also satisfy two properties of linearity, but they are functions. So we can talk about their invertibility also. So now the question is, if suppose we have a linear transformation which is also invertible, then T inverse, and we, so as you said that there is a way, if f is 1 1 and on 2, then you can always find such a g. So this I'm not going to prove, but you know that there is a result which says that f is invertible. If I know, or you can prove this also, it's very straightforward. F is 1 1 and on 2. This is what you initially said. So I agree, this is true. Now the question is, so let me write this as a result. The question is, if we have a linear transformation and suppose that it is invertible, whether the inverse is also whether the inverse is also linear. This is the question. So the question is, if suppose we have a linear transformation from V to W, and if suppose T is invertible, if T is invertible, then T inverse is also a linear transformation from W to V. So if T is invertible, then the inverse is also linear. Alright, so how to do that? Just use the definition. So we want to show that we are given T a linear invertible map or linear transformation which is invertible. We have to show the inverse is also linear. So we just use the definition of linearity. So what I will do, I'll take two elements in W, say W1, W2 in W, and I will take a scalar, let's say alpha in F. F is the underlying field. And what to show now? To show that in order to prove that this is linear, I will show that T inverse alpha W1 plus W2 is equal to alpha times T inverse of W1 plus T inverse of, right? This is what I need to show. Now how to do that? So we know that T is invertible. So T inverse exists. So T inverse of W1. So let's say T inverse of W1. This would be some vector in V. So let's say V1. And T inverse, similarly T inverse of W2, this would be some vector in V. So let's say V2. Then since it is invertible, we know that W1 is actually the unique image of the image of V1, and W2 is the image of V2 under T, right? This way, because T is invertible, I can just take the composition with T and then I'll get this. And then from here, now what I can say is that if I look at this T alpha V1 plus V2, what it is? I know that T is linear, so I can use the linearity of T. So it would be alpha times T of V1 plus T of V2. But then I know that T of V1 is just W1 and T of V2 is W2. But then I also know that T is invertible. So the alpha V1 plus V2, if I take the inverse, it would be T inverse alpha W1 plus W2. Because T is invertible, I can do this. But then what it is? It is the left hand side is one thing, the right hand side is one thing here, But the left hand side, what I can do here, it is just alpha times v1, but v1 from here, it is just
T inverse
T
W1.
inverse
Alpha
T
T
inverse
inverse
W.
W.
W1.
Yes, right. But then it proves that T inverse is linear. And we are done. So now if you look, go back here in this result, here, now what I can add here, I can say that F is a finite dimensional vector space and T is a linear operator. Then T is 1 1 if and only if T is onto, if and only if T is invertible. Because 1 1 onto implies invertibility, or it is equivalent to invertibility. So in general, you can write it in this way also. So let me add this condition also. So you can say that, let us write this, add this condition also. So it would be, if we have a finite dimension vector space and if T is a linear operator on V, then following are equivalent. So TFAE means the following are equivalent. So what are they? T is invertible, T is 1 1, and T is 1 2. And this follows because of rank nullity theorem. Are you agree with this?
Yes, sir.
Yes, sir.
Okay, fine. Now, as I mentioned that this is true, here the assumption that V is finite dimensional is important here, because if it is not, then this result may not be true or need not be true. Now, why this is? So let us take this example first. So let me write this here. The above result fails if V is infinite dimension vector space. For example, let us take the first example. Let's take T from the set of all polynomials over R to set of all polynomials over R. Okay, and you look at this function. Okay, now first tell me whether T is linear or not. Take
Yes,
any
sir. It is
polynomial and set
linear.
it. It's linear, so clearly T is linear. Is it 1 1?
Yes, sir.
Is it 1 1? It's 1
Yes,
1?
sir.
No, sir.
Why? Okay, so we have to answer. So first tell me why not, and some of you are saying yes, so you justify each other. Yes, so why, first you tell me why this is not, or first you tell me why this is a linear, this is a 1 1 map, so that the other student can point out any mistake if there is.
Sir, if we are going to take the basis element PR of as 1x square and in such a form, then their map is going to be going to be, sir, uh, x, x square and xq, like that, x square xq, and it will be plus 2 probably added in each term,
So
and set, and they are linearly independent, sir.
So what?
Sir, the representation of G, if T0 is equal to 1, T0 contains only one element, sir.
P0 contains only one element, but your justification is not precise here. So you are saying that you are, so you are trying to show using the basis, which whatever argument you gave, that is not complete. I agree that if you show that null space of T is just the zero space, then it is then it implies that it is 1 1. So instead of proving that using a basis, because it's an infinite dimension. So the argument you are giving is not complete. So what you can do is that you assume that there is a non-zero element. That way you can show. So let's say assume
Yes.
that if I just follow
Uh,
you, let me finish with him. Let me finish with him so that he can understand. So let us take a non-zero element in the null. Or let's say let's take an element in the null space. So let's say x square px is equal to 0. Assume that this is the thing. Then you have to show that px has to be 0, right? Then
Yes,
you
sir.
are done. Then you are done. Now x square px equal to 0. What
सर
does it mean?
इसमें जितने भी कांस्टेंट वाले फंक्शन हो गए ना सारे 0 पे मैप कर जाएंगे, इसलिए 1 1
Constant
नहीं
wale?
होगा. यस सर,
No,
अगर
no,
हमारा
just
पोलिनोमियल
no. I'll come to you. I'll come to you. Let us finish first his argument. Let us finish his argument first. So x square px equal to 0. You also follow and tell me if I'm making any mistake here. So x square px equal to 0 by definition. So my aim is to show that px equal to 0. Now how to show that px equal to 0 from this? Anyone? Since px is a polynomial, any polynomial I am taking, so it will have some degree. So let's say, I don't know what would be the degree, but it will be a polynomial, let's say of degree m. So it would be, let's say, a naught plus a1x and so on up to am xm kind of thing. This is 0. But then this implies that a naught x square plus a1 x cube and so on up to am xm plus 2 equal to 0. But does it imply that all ai's are 0?
नो सर.
Why not?
Yes.
It will imply, sir.
It will imply.
Yes, sir.
Yes, sir.
सर ए नोट वाले कांस्टेंट को 0 होने की जरूरत नहीं है ना, क्योंकि अगर
No,
a1
no,
a
no. You forget about your argument. You just tell me from this equation. Up to this is fine. Do you agree with me? Whatever I
Yes,
have
sir.
written so far, this is it. Now, from here, can we
यस सर,
conclude
इसके
that all
लिए
these coefficients are 0?
Yes, sir. Yes,
अगर
sir.
यस सर,
x खुद
यस
ही
सर, 0
जीरो
होना.
हो गया सर, तो
We
फिर तो
can
ये
just
जीरो बनने जाएगा ना, तो ए आई नॉन जीरो ले लेंगे तो भी जीरो बन जाएगा.
So there is a problem now in your arguments.
sir.
See here,
You
this is a polynomial. So if we are saying that this is 0, that means this should be 0 for all x. X are coming from R, the field. So this implies that all these AIs are 0. If all these AIs are 0, that means what? That means Px itself is 0 because this is our Px. So this implies that Px is 0. But if Px is 0, then you know that it is actually the null space of T is just 0 space and therefore it is 1 1. Now the why you are missing the argument is here. So let me in order this might be useful for your understanding whatever I'm going to write here. How to show that these elements, let's say these 4 elements are linearly independent. So these 4 polynomials are linearly independent. Just tell me how to show that they are linearly independent.
We take the linear combination of
सर लीनियर कॉम्बिनेशन में
C1
स्केलर
plus
सोर्सिंग
C2
दिखाना
x
है.
equals
Yeah,
to
so you
0.
are saying that you take these and then show that then put them equal to 0. Now you have to show that all these scalars are 0, right? Now why
Yes,
they
sir.
are 0?
सर क्योंकि
Compare
पोलिनोमियल 0 पोलिनोमियल के इक्वल है
equals
ना.
to 0, 0
0
into
प्लस 0 x
1
प्लस
plus
0
0
x
into
स्क्वायर.
x plus 0 x square plus 0 x cubed.
So
Then
it's
compare.
equal to a 0 polynomial. Now if this is any of this is not 0, then we have something which is a 0 polynomial, which is like we have a different a different 0 for the space of polynomials, right? Which is not true. So
Yes,
all of
sir.
them has to be 0. This is one way. So this is equal to 0 polynomial, but 0 cannot be 2. So this has to be, all these scalars has to be 0. This is the first argument. The second argument is that since they are polynomial, so this expression should be should be true for all x, right? Where x is is in R, because this is again a polynomial. So if I put any value of x, then this will if I put some any x, so what I'm saying is that whatever I have written here, this is 0, this is 0 for all x is in R, if I want to say this, because this is again a polynomial, so this should be R. But if this is 0 for all R, now if any of these AIs are non-zero, then how many roots it will have? If any of these AIs are non-zero, then it will have more than 3 roots. It will have infinitely many roots, but it is not possible for a polynomial, and therefore all of them has to be 0. This is the second argument you can use.
So why
Is it
infinitely many roots?
So less.
because if so it is like so if you consider, so if suppose it is a polynomial over C, let's say, first of all, if suppose it is a polynomial over C, then by fundamental theorem of algebra, do you know what is fundamental theorem of algebra?
Every algebraic equation has a root.
So that means every polynomial is also an algebraic equation. It has a root, and if it is of degree n, so every polynomial of degree n has exactly n roots. If p is a polynomial of C over C, so p is a non-constant polynomial over C, then it will have a root. But using this, you can also show that every polynomial over C of degree n has exactly n roots. So if we consider this, let's say, if I change, if I consider P over C instead of R, then you can also use this argument by fundamental theorem of algebra. So what I'm saying is that if you consider this in the same example, if you consider this space, then you can also use fundamental theorem of algebra in order to show this. You just look for this, what is fundamental theorem of algebra. So let me write what is this. So those who are interested, they can just look for it. Okay, what is fundamental theorem of algebra? Fundamental theorem of algebra. What it says is every non-constant polynomial over C has a root, or equivalently, or from here you can also say that every these from here you can also conclude that every polynomial over C of degree m has exactly m roots. All right, so this also you can use if P is over C. If P is not over C, then instead of fundamental theorem, you can just say that it has because it is equal to a 0 element, but there cannot be 2 0 in a vector space. So all these scalars has to be 0. So this map is 1 1.
सर
So
एक्स की वैल्यू पुट करके भी कर सकते हैं ना, डिफरेंट एक्स की डिफरेंट वैल्यू पुट करके भी कर सकते हैं ना, इक्वेशन बन जाएगी.
that yes, that you can do, provided, but in that also actually you are using the fact that this
इज इक्वल टू 0
algebra
तो ए नॉट इज इक्वल टू 0 आ जाएगा. ऐसे मतलब कि एक्स की वैल्यू पुट करेंगे तो हमारे पास इक्वेशन बन जाएगी, फिर उससे इनको दिखा देंगे कि ये 0 के इक्वल होंगे.
Right, so that way also you can do. I agree, that way also you can do. So this map is, so this T is linear, it is also 1 1. So we have checked linearity, we have checked 1 1ness. How about ontoness? Is this function onto?
No, sir.
Why not?
No, sir. कांस्टेंट फंक्शन की प्री
Degree one
Constant.
polynomial.
Right. Constant doesn't have any pre-image, so not onto. So that
Pre-
means this function is not invertible. So you see here, if t is if it is from an infinite dimensional vector space, it is an operator on an infinite dimensional vector space, then the previous result which says that one-oneness, onto-ness are equivalent to invertibility. This is not true if we have an infinite dimensional vector space. Similarly, if you take this example, second example, let me give you. It is you take all sequences over f. F is either R or C. Okay, so let me just precisely write R. Okay, and how it is defined? It is right shift. So x1, x2, and so on. If you take any element in here in the domain, it would be of this form. Then you send it to x2, x3, and so on. Now you can verify again that this is linear. How about one-oneness? Is it 1-1?
Not.
No, sir.
This is not
No,
1-1.
sir.
Why it is not 1-1?
क्योंकि
x1 is arbitrary to
x1 वाले जितने भी एलिमेंट्स
Sir,
होंगे वो
X1
सब
different
indeterminate
values.
two different element maps to
Yeah.
same.
X1 you can take any value to x1 and to keep other elements same, and they give the same image. But how about onto-ness? Is it onto?
Yes, sir.
Yes.
Yes,
So
sir.
this is onto. So linear onto but not 1-1. So implies not invertible. So the result which we stated that 1-1 and onto-ness, they are equivalent. This is true when we have a finite dimensional vector space. So let me give you an exercise and then we can move to the next topic. So we know that if V and W are finite dimensional vector spaces, and if T is an invertible linear transformation from V to W, then the inverse is also linear. Since inverse is also linear, we can also inverse is a linear transformation, so we can also talk about its matrix representation, the matrix representation of the inverse of T. So the question is, what is the relation between the matrix representation of T inverse and the matrix representation of T? So this I give you as an exercise. What is your guess? Can you guess something
T
here?
inverse is equal to A inverse.
Yeah, so if A is the inverse, A is the matrix of T with respect to B and B dash, let's say, then the inverse of T would be the inverse of A. Inverse of matrix of T inverse, or sorry, so the matrix of T inverse would be the inverse of A. So this I give you as an exercise. So if T is a linear transformation from V to W, let's say this is linear, and assume that it is also invertible, and assume that we have a basis B for V and B dash for W. Okay, these are bases. Then the matrix of T inverse with respect to B dash and B is equal to the inverse of matrix of T with respect to B and B dash. Okay, so this I give you as an exercise. All right, so using this result, you can actually now you tell me, if I give you a matrix of a linear transformation, then can you find the linear transformation? For any linear transformation, if I give you I give you that okay, this is the matrix with respect to this basis of T, tell me the T. Can you do that?
Yes, sir.
Yes,
It's
sir.
easy to do,
Yes,
right?
sir.
You know how to find the linear transformation from the matrix. You know that we have made this observation in the previous class. So if we are given a matrix representation, then we can always find a T for which the given matrix is the matrix representation. And since now you have also proved in the class here that in today's class you have proved this linear this function also. So it says that if you have a matrix, then you can always find a linear transformation such that g of t is equal to the given matrix. But since this is an isomorphism, that says that you can always do it uniquely. That means for a given matrix there is a, and if you fix the basis for a given matrix, there is a unique t such that the matrix representation of t is the given matrix, right, from here. And therefore if you want, you have to find, let's say, inverse of t, then in some cases this result may be useful here. So sometimes it is not easy to find the inverse of t, although it is easy to prove that t is invertible by checking one-oneness and onto-ness, but finding inverse may not be that easy. So in that case this result may be useful, not always, but in some cases it may be useful. Like you just find the inverse of you find the matrix of t. If you can, then find its inverse. If you can find the inverse, then you know what is the, because of this result you know the matrix representation of t inverse. Once you know the matrix representation of t inverse, you can easily find t inverse. All right, for example, let me give you this example here. So you complete this example. Okay, so I give you this as a problem, let's say. So I give you this problem. So use above result, find the inverse the following linear transformation. What is this? So T is a linear transformation from R3 to R3. How it is defined? You take any vector in R3, which I'm writing as a column vector, and you send it to this vector here, x1 plus 3x2 minus 2x3, 2x1 plus 3x2, x2 plus x3. Okay. So what you have to do here, you try to find linear transformation inverse of t both ways. So that will like clear your idea even more. So what you do, you first find, so there are two ways you can try. So first idea is that you just find matrix of t with respect to any two bases you can take. You can take the standard basis here. You just find the matrix of t with respect to, so you have to fix basis for R3. So you find matrix of t with respect to V and then find its inverse. That would be the inverse, that would be inverse of or the matrix of T inverse. The second idea is that, and then once you have the matrix of T inverse, then from that you can find T inverse. T inverse. Second idea is that you just try to without using this matrix representation, you from the map itself, as you do in general when how to find the inverse, you try to define a function g or the a function from the codomain to domain and try to see if that is that serve as a inverse. Okay, so this is by using the definition of T inverse. So these two ways you can use to find inverse of. All right, so we got some time. So let me. So do you have any doubt so far? So after the quiz, yes.
सर इनफाइनाइट डायमेंशन वाले के लिए भी मैट्रिक्स निकाल सकते हैं.
Infinite dimension के लिए मैट्रिक्स कैसे लिखोगे? So there is some notion. So there is some notion of infinite matrix which are like of this form. So up to this you know entries, and then the rest of the entries you say that okay, they follow some pattern, and then you can write. There is some notion, but it's generally we talk about matrices when we have like a finite dimension thing. People try to extend this. There is some notion of these infinite matrices also, but not for this course. But you can, of course, you can, if you want, if you are interested, you should look into these infinite matrices also. In some books, they like for infinite dimension vector space, they also, we cannot say that it is the matrix representation with respect to something, but you can talk about infinite matrices. But as I mentioned clearly at the beginning, you can write like this matrix representation for finite dimension. For infinite dimension, things are not that straightforward. All right. So any other thing? So there may be some students. So just let me clear. So whenever I try to make the class more interactive by asking you the questions, and some of you are also participating, that is good. But there may be some students which are like which are lacking the discussion here, because only like a few of you are like participating in the discussion. But there may be some students which are, let's say, which are hesitant, or which are like not that confident to speak, or they are shy. They know or they don't know, but they are shy to speak. So for such students, try to speak your doubts, try to tell your doubts. Then only I will know that you have some problem in understanding. If you don't ask, then I will assume that all of you are getting like all of you are on the same page. If you have doubts, if you don't want to like discuss in the class, during the class, you can write me an email. I will try to arrange like a separate session for you. But you will have to come forward. I don't know. I mean, I don't have any way to know that you have any you have some problem related to the course. Okay, so please come forward. If you have doubt, don't be hesitant. We are here to help you, and you are here to learn. So it will only be fruitful if you like participate, or if at least you communicate your problems. So tomorrow would be your first quiz, and there would be many more exams. So here itself, you try to like make things clear, then it will help you, because this is the basic course. And then in the next semester in next to next semester, there would be some advanced courses. And if here itself you are hesitant, then you would be keep hesitating in the other courses also, and then like it is your loss. So you are not losing anything. We are not here to show that I know more, or you know less, or you know more, I know less, or some. We are not here to. We are like, if we keep it like friendly and move forward, then it will like help you, and I will also be like happy in that way. So keep forward, tell your doubts related to the course, and make sure that you are understanding all the things, because these are the basic stuff you will be needing in all the courses, this basic linear algebra. And we are only learning basic things only. So basic mathematics we are trying to learn, how to write, how to speak, how to like say something mathematically. So any doubt, then you can ask. Anyway, so let us define linear functionals now. Now, so far, whatever topics we have covered, like this linear equations, vector space, subspace, basis, dimension, then linear transformation, these things might be like you might be you might have learned these things in your graduation. May not be in more like that detail, but at least you are familiar with these terms. The next topic may not be familiar for you, or it may be, I'm not sure, but it may be new also. So let us start this topic. It is linear functionals.
So,
Yes.
So actually, there are some students who's going through their undergrad final exam. So can we have minor of LA on 25?
So no. What do you mean by undergrad? Okay, so that means
BSc, BSc, sir.
BS. So BSc result is not out yet.
No, sir.
So
No, sir, even
I mean,
exams are going on final.
exams are going on. Oh, okay, I was not aware of this. I don't know. So I think this I cannot take this call at this point because I'm not the right person to take a call on such issues. So what you can do, you should write to like administration, like your dean, faculty, or whatever email is given to you. You should write to the right person, and then you ask that you are having these exams. The graduation exams are going on. They are not yet over, and there is some clash between the dates, and you want to shift it to some other date because there is a institute timetable which is already out, I think, for minor exam, and we have to follow that. What we can do is that if like we can shift it to 1 or 2 hours, like on the same day, but it's not like we cannot like postpone it to some other day. Like it's not advisable, so it's better to take their permission. If they allow, if they agree, then I can do that. I don't have any issue, but the decision would be theirs, not mine, because I don't know who, like in what state the exams are not yet over, and I cannot take this decision also because I'm not the authority to take this. So you just write to him, to the dean faculty, or not dean faculty, dean academics, and then hopefully they will reply in your favor. Any other
Okay,
thing?
no, sir. Okay, sir.
Okay, fine then. Okay, so let us define what is linear functional. I have already defined what is linear functional. A linear functional is a linear map from a vector space to the field. It's called a linear function. So if V is a vector space over F, okay, then a linear map from V to F is called a linear functional. So here in this section or in this topic, I will mostly focus on finite dimensional vector spaces only because the infinite dimensional version of linear functionals and these things you will learn in functional analysis. Okay? So just to keep things simple and like to understand them in a better way, we will keep assuming that V is finite dimensional. Anyway, I will every time I will mention, but there are some things which can be generalized to infinite dimension also, but there are some things which we are not able to do in infinite dimension. So V is a vector space over A, then a linear map or linear transformation. So I'm using the same meaning for two different words, map and transformation. So if you want, I can write it linear transformation. So a linear transformation from V to F is called a linear function. So what is the notation we are using for this? So we know that the collection of all linear functionals, this is the notation so far we have been using. So linear transformation from V to W, here W is F. So it's V comma F. So what it is the collection of all linear functionals. That means F is linear. Now for this, I will use this notation V dash. If V is a vector space, then V dash is the dual space, or is the set of all functional, and it is also called as dual space of V. Okay, so if we have a vector space, then collection of all linear functionals is called dual space. All and it is denoted by V dash. Now you tell me if V is finite dimensional. So far I have not assumed that V is finite dimension. In the definition and in the notation I have not used anything. Now but if suppose if V is finite dimensional, what can you say about V dash?
V dash is also a finite dimension.
Finite dimension.
Finite dimensional, why?
Sir, it depends on field.
So you tell me if V is finite dimensional, then you said V dash is also finite dimension. If it is true, if you are saying this, then you have to justify your argument.
Sir,
Why this is?
since in we are going to take F as a vector space in F only, then it will be one dimension.
So
And sir, V is a finite dimensional space. Then the LVF will be of dimension of V cross dimension of a the dimension of V cross 1.
V cross 1, so it is dimension of 1. Dimension of V, sorry.
Yes.
Yeah, so that is true. So we have already proved this in today's lecture. No? If you go back again, we have proved that, look at here. So what is the dimension of this LVW?
M into N.
M into N.
Because we know we have proved that if V and W are finite dimensional, or if and only two V and W are finite dimension, if and only if there is an isomorphism between them. We have an isomorphism, so dimension of this is equal to dimension of this. We know that dimension of space of M cross N matrices is equal to M times N. So same would be for this. Now here I haven't assumed anything on W. So W can be any vector space. In particular, when W is F, the field, then the dimension of LV comma F is, now you look at in this way, this would be just dimension of N.
M.
So if V is finite dimensional, then the dual space of V is also finite dimensional. All right. If V is finite dimension, then we can say that V dash is also finite dimension. Not only that, we can say that
और बता दीजिए
सर फील्ड की डायमेंशनिंग तो फिर देखनी पड़ेगी ना फिर
yeah, so here if so okay, so you can say up to this at least you can say clearly, right? If V is finite dimension, then V dash is finite dimension. What is the doubt? Why the dimension of field is coming into picture? What will be the dimension? Can it be infinite? So here we are talking about, let's say, if V is finite dimension, and V is a vector space over F, can F be infinite dimension? So I'm saying that V over F is finite dimension. Huh?
F over F has dimension
F.
1.
Yes.
So field. So we, when we talk about the linear transformation, we say that they should be of the over the same field, right? Both the vector spaces. So whenever you only told me in the at the beginning when I was defining the linear transformation, before I said you only tell that V and F should be over the same field F. Then only we can talk. Now here this V dash is what? V dash is the collection of all linear transformation from V to W. But here in particular our W is this. Now if V is finite dimension, then definitely V dash is finite dimension.
यस सर फिर F की डायमेंशन 1 होगी
Right? So
यस सर फाइनाइट डायमेंशन यस सर V is
dimension
finite.
yes. And dimension of V is equal to dimension of V dash. All right. Okay, so for example, let me give you first some examples. You can verify that they are linear functionals. and then I will make an observation. So I still got 10 minutes. So let's see whether we can do that or not. For example, if I take this trace function, what it is you take any matrix of size n cross n and send it to its trace. What is trace? Trace is the sum of the diagonal entries. Assume that A is of the form Aij. Now this is a linear transformation. This is a linear transformation. So this is actually a linear functional. Similarly, you can verify this because I don't have time and they are very straightforward. Let us take this linear function on an infinite dimension vector space. This is what? This is the set of all or space of all space of all continuous functions on closed interval ab to r. Okay, so real valued continuous functions on closed interval ab. And how the function, this int function, this integral function is defined? You take any function here and send it to this definite integral. Now this is again a linear functional. This is also you can verify. Let me give you one more example. If I fixed any t in f, where f is either r or c, set of real numbers and complex number, then for any fixed element t in the field, I define this linear transformation from the space of polynomials to f. What it is, you take any polynomial here and send it to its value at point t. So what it is actually evaluation of the polynomial at t. Now this also you can verify that this is a linear function. All right, so this you can verify. I'm not going to verify, just you have to check that they are linear function, linear transformation from this space to this space. Okay, so let me make an observation here. So I want to define dual basis of the dual space. But before that, let me make this observation. So observation first. So if suppose we have a finite dimension vector space, let's say we have a finite dimensional vector space, and assume that n be the dimension of V, or you say that let's say this is the basis V1 to Vn. This is a basis of V. Then you tell me whether whatever I'm writing, whether that is correct or not. Then for each I there exists, you have to tell me why there exists a unique functional, linear functional, let's say fi in V dash, such that fi of Vj is equal to this Kronecker delta del ij. That means what? That is 1 if I equal to j and 0 if I is not equal to j. Now tell me why, if whatever I have written, whether it is true or not, and if it is, why it is true. So we are given a vector space, we are given a basis, we have also fixed a basis. Now I'm saying that for each I, where I equal to 1 to n, so let me write I equal to 1 to n, so I is I equal to 1 to n. So for each I, where I is from 1 to n, for each I is from 1 to n, there exists a unique functional fi such that fi of Vj is equal to del ij. Now tell me why this is true, or if it is not, then why it is not.
सर वीजे का कोऑर्डिनेट्स होंगे जो मैट्रिक्स रिप्रेजेंटेशन में वो यूनिक होगा और उसी पे मैप कर देंगे.
Okay, so you are saying, so you tell me this function. So let's say you tell me f1. What would be f1? You know that there is a way. So we have done this, right? Why are you not able to answer this? So we have done this. We have a vector space V. We have a vector space W. If we fix a basis V1 to Vn, and if we fix, let's say, n vectors in W, I don't know what is this W. This W can be anything. I will fix these n vectors. Then I can always find a unique T such that T of Vi equal to Wi. This we know. Now in this case, what I want that this Fi Vj should be equal to del Ij. So this Fi is actually linear and this W is my F here. Now what for V1, for F1, what should I choose? What Wi I should choose? So if I want to define F1 here, F1 from V to F, such that Fi F1 Vj is equal to 1 if j is equal to 1 and 0 if j is not equal to 1. What would be my Wi's? So here I know that if I take 1 0 0 0, then I know there exists a unique linear transformation from V to F. That means a unique functional, such that f1 of Vj is equal to 1 when j equal to 1 and 0 if it is not. So I have used that result. Is it true? So whatever
Yes,
I
sir.
have written,
Yes, sir.
so it
Yes,
makes
sir.
sense. We have done that. Then you should be able to answer this then. But then there is nothing special about f1. You can do it for any I.
Fi.
So for each I, you can say that there exists a unique Fi because of this result, such that Fi of Vj is equal to del Ij. Fine. This is the first observation. Now, under this, you can say that, so this is the first thing. Then, if I take any,
Sir, the next class है और 1
okay,
minute
okay.
ही.
Yes, yeah, I understand. Okay, so we can stop here. So in tomorrow's lecture, tomorrow's quiz, the syllabus is everything we have covered so far, except this dual basis, the last thing. Okay, I will also send an email regarding that, reminding you the quiz tomorrow. I'll also share some more details. So you do your best, try to finish it on time, follow the instructions strictly, and upload your answers on time. Try to assign every page the right question. Okay, so we can stop here now.
Thank you, sir.
Thank you, sir. Have a good day.
सर
थैंक यू
Yes.
सर.
सर आप नोट्स MS टीम्स में अपलोड कर सकते हैं इंस्टेड ऑफ मूडल.
MS Team में I haven't done that, but I think there is a way to do. So I can. So Moodle, is there any problem in opening Moodle?
यस सर मेरे फोन में वो ओपन नहीं होता है, मतलब मेरे को नोट्स मिलते नहीं है मूडल पे. मैंने बहुत बार को इंस्टॉल भी किया, फिर वापस से इंस्टॉल किया, बट ठीक नहीं हो रहा है वो चीज.
अच्छा ठीक है. So I'll see if I can do it on like Moodle. If not, then I'll send send you on email. The PDF file I will send on email. Is it okay?
थैंक यू सर.
To all the students. Okay, fine.